Okay, we continue now. Can you hear me? Okay. Thank you, Virginia. We continue. So now we'll use another now we are going to talk about a boundary value problem. So boundary initial boundary value problem. So now we abandon the idea of periodic boundary conditions, and so instead of treating this case, we want to treat this case. So we have a region, and we want to put some conditions here, if needed. So we want to solve here, okay? So this point is no longer identified with this. So for instance, if we are solving for dtu equals dxu, so a equal to 1, let's put a here, and just say that a equals to 1. If a equal to 1, then we know that the solution of this is just the initial data. We were working on this t plus x, because if we take the derivative here, we get a prime here, and on the other side we get a prime also. Okay. So and this is so the value, if we have some value here, some, say, let me write in green. If we have some values here for the, so I'm drawing this in the same plane as this, but it's actually in another plane. Let me draw it better. Well, I'll do both. Let's do this first. If we have some value here, this value is going to be constant along this line, right? Because when, suppose this value is x0 here, so at t equal to 0, here I have u0 of x0, and this line is the line where t plus x is equal to x0, so is the line x of t given by x0 minus t, okay? So goes for the negative t, x. So and if we are here, say up to here, we have a solution. Up to here, we have a solution up to here, and so on. They are supposed to be, let me draw a bit better this. So these are straight lines, 45 degrees, okay? So I have a solution. If I draw it again here with more time, we have a solution in this quadrant, okay? We have a solution here. Wherever I have here a solution, it goes this way with the speed 1. So here the solution is unique and is given by the initial data u0, right? This. So we prescribe at t equal to 0 u of 0x equals to u0x. But we don't know the solution here, right? We know that to get a solution here, since the solution is constant along these lines, we know that if there is a solution here, it should be constant along this line. So what we have to give is the value here. So on top of that, we have to give u of TL. Let's say we are solving between t0 and L. U of TL, some function g of t. So we have to prescribe the values here. The physical interpretation here is you provide the initial data for the wave, and here also you provide the data that will be the wave, like this, okay? And there is, if you want a smooth solution, there is a compatibility condition that says that u0 of L should be equal to g of 0, okay? Because in this point, what you have here should be equal to the, so the line that goes out from the vertex, so these are supposed to be the same. These two lines should coincide. Otherwise, there will be a discontinuity, which is okay. You can think of a solution that has some discontinuity. So this is needed if you want some smooth solution. Okay, but notice also that here you cannot give anything, right? Because the solution along this line is determined. Okay. If you were doing this for a equals to -1 or a negative in general, then the solution would have gone this way, and so for that you have to give the values here, okay? So a positive, give values, you give u0, sorry, no. A positive, you have to give ut at the right side, some values, and a negative, you have to give u of t0 equals to g twiddle of t, okay? Depend on that. Of course, there are cases where, for instance, if I take an A, that does something like this. I is, let's do first, is positive in this side and negative in this side. This is L. Then, since it's negative here, I don't have to give anything here. The wave is going out here. And since it's positive here, the wave is going out here. So I cannot give anything here, or cannot give anything here, and then I don't need to give any boundary condition. On the other hand, if I take an A that is the other way around, then in this side there is an incoming wave, so I have to give g of t here, and in this side is also incoming, so I have to give g twiddle of t. Okay, that can happen. Also, it can happen that A can become 0 or being 0 all the time. for some systems. So it can happen that A is, say, 0 here, and then goes like this, for instance. So here there is some incoming wave. I have to give data, but the waves, what they do is they stop. So if you follow the vector field, they do like this. Okay, never reach this point. So the wave goes like that. And here you don't have to give anything because it's already determined by the value in the boundary. So at the boundary, dt of u at t 0 is 0, so it's control. In real life, things have become difficult because you can have some system now. Okay, what happens if you have a system? Then from this, you will say, okay, I have to look at this, what are the eigenvalues of this thing in the boundary. So I have to look at this equation. So my equation is like that, something like that. And I have to look at the eigenvalues of this in the boundary. So with respect to when I look at the boundary, and the boundary I have to replace the derivative by the normal to the boundary. Okay? So the thing that goes like this. Let me call something else. Let's call it big N, so that we don't confuse with the N that is the normal to the initial surface. N. So it's a covector, right? Because this is a surface, so the surfaces are denoted by covectors, not an arrow. I draw this as an arrow with 90 degrees because I'm thinking that there is a metric, but in general, in the theory, there is no metric. So the right thing is to have here a covector. So I look at this metric then. And this is the same, this is basically an alpha dx. If you are in several dimensions, suppose you are in a box like that with coordinates, say x and y, and you are here, this thing is the coordinate that is constant along this line, and these lines that is a surface is constant y moving x. So dy is the right quantity. So in this case, this is just dy. Okay. So this is it will be the component 2 of the vector. So I have to look at this matrix. This is in this case, okay? If I'm here, I have to look at the component 1. And notice that this dy already has the correct sign. This is pointing outwards, right? Here we have to take the one with the minus sign because we are moving. This is the outward direction. So this side we have to look at the minus dy. So you look at, but say we are just looking at this boundary here. So we look at this matrix, and this matrix has some, you can diagonalize it because we saw that they can be diagonalized. So this will have in the basis where it is diagonal, you have a lambda 1, so on, lambda s, lambda s plus 1, until lambda n. And you say the first ones, let's say you order this so that these ones are negative and these are positive from here. So these are positive. Okay? So like in the case before, for the A positive, we are solving, we have to give data. So in the basis where this is diagonal, you have to provide, let's call the base, the components in the base like twiddle alpha of t y equal to L, say, will be some function g alpha of t. And you can mix, of course you can mix things. This is the simplest thing. We'll see in the examples. And you don't give anything about that, right? So your boundary conditions are here from alpha equals to s plus 1 to n. This is the boundary conditions. Of course, there could be here that there is another line that has zeros, right? So the zeros, in principle, you cannot do anything, and they sometimes create problems. So we have a theory, a complete theory, when there is no zero here, and when there is zero with some conditions, you have a theory, and without those conditions, you don't have a theory. So these zeros here are problematic in some cases. So that's how you treat, in practice, how you treat. For instance, let me show you something. Suppose you have the wave equation, right? The second order wave equation. You have a phi, let's do in 1 plus 1. 5 dt minus 5 dt plus 5 xx equals to some rho. Okay? So this you can write first as b phi t equals to b, and then this equation is b, let's use this notation, is equal to, so I put on the other side, this is phi x of w, where w is 5, the derivative of phi x, and then you have the dt of w is dx of b, okay? Because if you take dt of w, this is dx, dt of phi, I can interchange the derivative, and this is dx of b, okay? So you have this system. This doesn't have derivatives, so this is not really important. So you look at this part, and this one you can diagonalize. You look at let's say u1 is b plus w. Let's say u plus u minus is this, and then you see that the t of u plus minus is dx of w in the first, plus minus dx of b. So this is dx plus minus dx of b plus minus w. So this is plus minus dx of u plus minus. Okay? So you diagonalize in this base. You have a dt of u plus equals to u dx of u plus. So it's a wave going this way. And the other one with a minus here, so it's a wave going that way. So for instance, you can do, of course you can say, okay, you are solving in some region. So in this side you will give something for u minus equals to g minus, say, and in this side you will get u plus equals to g plus, some boundary conditions, and here, so this is here, and here you give both u minus equals to u0 minus, u plus equals to u0 plus. Okay? This you can understand. In here the metrics, if you do use alpha, beta, I, and I, with this is the normal here, all the eigenvalues of these metrics are positive and real and positive, because we know that when you lower the index of this with a symmetric thing, this thing is going to be positive. So the eigenvalues of this, if this is positive and the eigenvalue of these are positive, must be positive. Okay? If this is going to be positive. So here you have to give both. And here there is only one that is positive, so you give this one, and here there is only one that is negative. Is positive, you give this one. Because in this side, remember, you have to multiply by dx, which is the outgoing normal, and in this side you have to multiply by minus dx. Okay? And that's why this sign change. There is a sign change here. So this, with this minus here, becomes plus, and you get this, the correct sign. Okay. So, but you can give some other conditions. For instance, you can give that in the right side, in L, x equal to L, you could give, instead of giving u plus as a function, you could give something like this. So when the wave goes, some wave goes here, from here hits here, there is an incoming wave. Let's use another color. You say, okay, at this point I will reflect the wave, so there will be an incoming wave. Okay? This yellow. So you can put here, if the reflection is total, I could use alpha equal to 1 or minus 1. If the reflection is partial, so that there is something is going out, so I could put here a smaller than 1 number, and so here the wave will be smaller. Or I could put in principle something big. But if I put something bigger than 1 here, this wave will be bigger, and so at the end, when I have many bounces, I will not have stability, right? Because I start with a small wave here, and through bounces it can become very big. So one have to be careful. But I can put something like that. And certainly in the other side here, I could put something like u minus equals to beta u plus, okay? For instance, plus g, something like this, g minus. The same here. So these are the possibilities, okay? So what about, how do I know this? I mean, this is okay. This is physically plausible because I compute the solution here and I know what I have to give to for having a solution. But what about stability? How do I know how to handle this? Well, let's look at the energy. Mm? And let me do okay. Let's do first this one. Let's do that. So let's look at the energy, right? The energy of these things is defined as u square, the integral between 0 and L dx. Okay? So if I take a time derivative, this is 2 integral 0 L of u dt of u, and this, using the equation now, is 2a integral between 0 and L of u dx of u, and this is a times the integral between 0 and L of dx of u square, and this is a times u square in L minus u square in 0. Okay? And in the periodic case, we use this to say, okay, this number is the same as this number because we are in periodic data, so this should be 0 and we get a conservation. But here we don't get a conservation, right? We have that whatever is in UL is increasing the energy, and whatever is here is decreasing the energy, right? So if I want to have a bound on the energy, here I don't need to do anything because this is negative. It's a negative number because, say, I'm taking a positive. So what I have to give is this. Okay, so if I say, okay, dt of dA is less or equal than a times, if I say this is g of t, right, at t square. So I have a energy condition with this thing. Okay? So this is, I have stability, right? Provided if I don't give this, then I don't have anything, because if I don't provide this data, this could be anything, so I don't have any control. So if I give data for this, boundary data, then I get a energy estimate. And this, you see, this doesn't play any role. This is what is the energy that the one is losing, and it's okay because this is the energy. We have waves that are going like this, and when they pass this line, they go away, so they don't contribute to the energy. So when I have the energy, say here, these contributions are no longer here because they went away. Here they were contributing to the integral, and here no longer. So these two are missing this way, okay? So here I will not see it. So I'm losing energy, so I'm seeing. The same, if I take a negative, then I have to give this thing. So in that case, I will get d dt less or equal to a times, now a is, okay, put this here, g of, let's call this gl and this g0 of t, okay? And this I don't have to give. So in both cases I get a contribution. What happens if I use the system, right, this system? If I try now this system. Well, these are there are two equations which are each one, they are decoupled, right? So I can define an energy now, which is the integral between 0 and L, and I will put u plus square, and then I will put here a constant, lambda, say, lambda square, let's go, so that you will know that it's positive. Each energy is conserved separately, in a separate way, so I can put a constant here. There is no problem, right? Because this is conserved and this is conserved. So when I do the calculation of the e to the t, I will do the same, so I will get at the end u plus square minus plus gamma square. I'm thinking about the sign of this thing. 1 second. Okay, let's do it. Let's do this. For this one, I have a plus 1, right? So I will get u plus square at 0, no, at L, sorry, minus u plus square at 0, and for this other I get gamma square, and I get a minus sign. I will put it outside, just outside, minus gamma square u minus square L minus u minus square 0. So I can suppose before I say, okay, I have to give this, which is positive, and I have to give this that is positive, okay? These I have to control. These two pieces are negative. But still I can do, for instance, as we say before, we say u plus in L is equals to u alpha, say u minus in L, okay? So this will give, this we say, okay, this is alpha square u minus square of L, and then I have this other piece here, minus gamma square u minus square of L, okay? And then I say, okay, I give this number, this I give g minus. So then I have plus gamma square g minus square of t. So we're given in the here we are given g minus of t, and here we are saying that the wave that is incoming is the wave the outgoing is incoming with some alpha. So here we are given u plus the, the incoming is equal to alpha u minus, which is the outgoing. So you see what we need here to have stability is to choose, I cannot go further. I already reached the just in, okay, I'll write it down here. This was alpha square minus lambda square times UL, U minus square at L, okay? So I need this to be non-positive. So I control and I throw away. So I will choose then I'll write it here. I will choose then gamma bigger than alpha. Absolute value of gamma. Gamma is well, yeah, I have to. I can change. Alpha could be negative, right? So what I want is an alpha to be lambda to be smaller than alpha. No, bigger, sorry. I have to choose lambda positive, say, bigger than alpha, okay? And in this case, this is going to be a negative number, and so I have the energy stability. So I can put anything here I want, any alpha. I just have to correct the energy to get an energy which is conserved. That might not be the physical energy, but it would tell me in any case that the system is conserved, okay? So I can do things like this. Of course, if now go to the other side and want to do the same, I will run into problems, right? Because I already choose this, and now if I want to do the outgoing be proportional to the incoming, then I have to check because I will get another condition and they have to be compatible for everything to be negative, okay? So this is the way, operational, this is what we are going to see. Now what we have to translate is all these inequalities, all this part, all this to the discrete level, right? We need to perform some calculation like this for the semi-discrete system. So when this is going to be tomorrow, when we write the equation dBn to dt equals, not Bn, sorry, for the vector, dB dt equals to some finite difference operator times b, a, say, we have to check what to do here, okay? So we have to do this. Now we have to think about what we are going to give here, because in this case we are not in the periodic case any longer, so when we are saying this point, we don't have this point to make the finite difference, the center finite difference. We have to use points in this side and the same here, right? We have to use points which are here, and we want this to hold, so we have to see how we are going to get this, okay? So tomorrow we are going to talk about this. Okay, so I stop now, and at 10 and at 5 after 11 we continue with Pablo. Questions about this? No questions? Okay, not yet. Okay. Okay. I need people to make questions, because then I know what they are understanding and what no, so I can go slower or faster in some topics. So it helps me a lot if I get uh, feedback from you. So try to make questions.